This experiment is looking at how grain size and slope affect the amount and type of liquefaction-induced lateral ground displacement that will occur. This is important because lateral ground displacement is extremely dangerous and can cause lots of damage to buildings and infrastructure, as you can see in image 1, but at the same time it is highly over-mitigated, which means that billions of dollars are being spent to mitigate this in situations where it's probably not necessary. The reason why my experiment in particular is important is because a lot of the research that has been done on this subject has been using computer models with extreme boundary conditions. These extreme boundary conditions are leading the computers to predict that lateral ground displacement will occur in slopes as small as 0.2 degrees. My hypothesis was that if I test 4 different grain sizes of sand, I will find that the grain size will not affect the minimum slope at which lateral ground displacement will occur, but it will affect the type. For this experiment, I designed and created this special chamber that allowed me to create the worst case scenario in all of the sand I tested. I would place water, then sand, into the chamber under controlled conditions, and then raise it to one of the 7 different angles that I tested. I would drop this hammer 30 times in 30 seconds, each hammer blow inputting an energy of 2.69 joules into my system. I collected data from my experiments using transparency paper on both sides, and I would draw the pre-test and post-test sand and water lines, as well as take measurements based off those sand lines. As you can see in the results section, the grain size did not affect the minimum slope at which lateral ground displacement will occur. They all experienced a minimum slope of 2 degrees, but the grain size does affect the type of lateral ground displacement. There are 2 main types of lateral ground displacement, and those are bulk sliding and lateral spread. Bulk sliding is when the mass of sand moves as a whole down the slope, while lateral spread is when it tends to more crack, flow, and spread down the slope. The 50 mesh sand experiences bulk sliding, while the other 3 types experience lateral spread, and then only in more extreme slopes, such as 5 and 10 degrees, will it experience both types of lateral ground displacement. In conclusion, these results support my hypothesis. The grain size does not affect the minimum slope at which lateral ground displacement will occur, but it does affect the type. This change in type is caused by varying soil factors such as ability to dissipate pore pressure and friction angle. The similarity in the slope is also caused by the friction angle. The friction angles vary enough to impact how individual sand particles will move, but not how the entirety of the sand mass will move. These results are important because they show us that to mitigate slopes less than 2 degrees is over-conservative and a waste of money. Additionally, we can use these results to better computer model lateral ground displacement in the future. Thank you for your time.